Okay. So like I said, I kind of turned around 15 and 14 because I want to talk about climates before I talk about changing climates. So when they talk about they've got data that suggests the atmospheric conditions are changing, and they say it's changing climate, then they must be kind of taking this rolling 30-year average and seeing changes in it. So one of the things, and of course we all are kind of a little familiar with this, that we know is that there's less ice coverage at the poles than there used to be. And so that would include glaciers, and that would also include like the oceans having ice on it, kind of like the Mississippi River, ice is over, the ocean's ice over, okay? And there's less ice than there used to be. So when we talked about numerical weather forecasting, we said basically you take these models and you give your computer these models, these programs, and then you have a bunch of initial conditions that you feed to your computer and run these models. Well, they actually have numerical forecasting for climate change too. If you watch the movie The Day After Tomorrow, right? Yep. You know that actually the hero, one of them he was a climatologist, which meant that he had models that studied changes in climates. So things that you might include in your model would be people burning fossil fuels, okay, putting out particulates and carbon dioxide and carbon monoxide, people building cities, okay, this all has to be in your model. Then we get to some kind of Mother Nature things. So like the sun could be doing some funky things. In the movie The Day After Tomorrow, that was one of the things early on. They're like, oh, well, is the sun doing something different? And the answer was no. Okay. We'll talk about kind of variations in the sun coming up. There could be just general trends in the hydrological cycle, changes in the hydrological cycle, changes in stuff that's in the atmosphere, okay, either man-made or Mother Nature, changes in cloud cover and with regard to type and amount, changes in outgoing radiation, and kind of related to that, when we lose our ice cover, it changes our albedo. So then our radiation that's going off changes. So some of this, though, is definitely, it's just very complicated. The biosphere interacting with the atmosphere. Okay, the atmosphere interacting with the ice, which we call the cryosphere. The biosphere interacting with the water. Okay, so all of this, each one of these boxes would have to be represented in your model as kind of a player. So it's complicated, right? If you want to think about climates, maybe are not that complicated, but the change that the climates might undergo, these are all kind of potential factors. So clear back in Unit 1, we talked about the different spheres. Remember, there's a hydrosphere, that's the water. There's the geosphere, that's the earth. The atmosphere is the air. And this is actually kind of in one picture showing you kind of the interactions. Biosphere, that's life. And back there with the mountains, you see snow, that would be the cryosphere. So climate change, well, in order to kind of think about climate change, we need to be able to go clear back. And if you take astronomy, you probably might recognize that 4.6 billion years ago, that's basically when the sun turned on. And our planets, kind of whatever stuff was going to make our planets was there to make our planets. Okay, 4.6 billion years ago. So the Earth has undergone some changes. Now, if we want to understand climates way back when, that's actually a field of study called paleoclimatology. So in order to understand climates way back need to use data that's called proxy data. And if you want, I'll put a star next to this. You can put a star next to it too if you want to. Proxy data is one of the terms that is actually on your review sheet for this chapter. So proxy data are like your ice cores, right? Proxy data are like sediment cores. Proxy data actually can also be tree rings, kind of give us a sense for what the growing season was like for a tree. Okay. So the next few slides is actually going to bring in two types of oxygen. So we have oxygen 16 and oxygen 18. And if you've had a chemistry class, you might know that actually oxygen is great. It has, make sure I get this right, actually all oxygen atoms have 8 protons, so I'll do this, 8 protons. And the difference between these two is this version has 8 neutrons, and this version has, let's see, 10 neutrons. Okay, so that actually is the difference between these two versions of oxygen. But my point is that those two versions of oxygen, you're going to see it on the next slide, this one is most abundant. Most abundant. Means that actually there's most of that heavier oxygen. Well, what does that have to do with climates and trying to track what sort of temperatures maybe we've had in the past? Well, here's a hint. That heavier oxygen, okay, I actually added the IE. That oxygen 18, the amount of oxygen 18 you'll see in rainfall or snowfall will decrease as your temperatures decrease. In other words, the amount of oxygen 18 that you'll see in rainfall will increase as your temperatures increase. And actually, this is temperature, down here this is temperature, and this is oxygen 18. So, back to the slides. So we talked about ice cores like you see in the movie The Day After Tomorrow. Well, aside from ice cores, there is on the bottom of the ocean floor, if you dig down in the muck and go farther and farther and farther, what you're going to be doing is going back in time. So this actually, if this is my ocean floor, okay, and this is my ocean water, actually we're going to see a rig here in a minute that basically can go through and it goes down and it gets a plug of this, okay, ocean sediment. And the point here is that this is going to be the oldest critters, okay, and this is going to be the youngest. It's like an ice core, but it's an ocean core. Okay, and like the slide says, you can actually, depending upon what the old organisms were versus the young organisms are known to have certain temperature conditions, and so you get a sense for temperature just with that. The other thing you can do with your plug is actually you can analyze it for those two types of oxygen, and I'm not going to necessarily hold you accountable to all these details, but I just want you in general to know that you can use that those two different forms of oxygen to understand what sort of temperatures were in place. So this is the rig that can go down and get that core I was describing. It looks like an oil rig, doesn't it? But it's a science rig. Yay, science. Boo oil. No.
No, we kind of need that.
Yeah, I agree. So that was sediment cores, okay? And the ice cores, again, back to the movie The Day After Tomorrow. That poor dude who actually, the whole, like, avalanche started when he sneezed or something. I don't know. No, I guess it was just going to happen.
Yeah.
Kind of a scary start to a movie. But ice cores are kind of like what I said before about the sediment, especially if you're going up into those kind of E sort of climates, those polar climates, where if this is your snow, you figure that's new snow, this is old snow, this is older snow, okay, this is like going down, okay, and so you just get a core of that, and you get all sorts of good information with regard to temperature. Because I'm going to show you some temperature data for climates, and this is just generally the Earth's climate, right, an average temperature for the Earth, going back in history, and you need to know how those are obtained. Another thing you can get with your ice cores is if there was like a volcano doing its thing, actually that layer at that time, you're going to see ash and that sort of thing. The other thing these ice cores trap are not just particulates like ash, but they also trap gases, which I think is kind of cool. So that's why we're going to have a slide coming up to kind of show you how much carbon dioxide there is in the Earth's atmosphere. Oh, there's always been carbon dioxide in the Earth's atmosphere. There used to be a lot more than there is now because plants actually came on the scene and converted some carbon dioxide to oxygen so we could breathe it. Wasn't that nice of them? But using ice cores is one way to find out how much carbon dioxide there has been at the Earth. So see, this doesn't look all sciencey. It looks very cold. Okay, so these are looking at ice cores. National Ice Core Laboratory. So we have a few slides kind of like this, and they have different scales along the y-axis down here. So this is thousands of years before the present. Okay, so that means that this is now right here. Okay, and this, for instance, is 5,000 years ago. This is 10,000 years ago. This is 20,000 years ago, etc. And along the y-axis, we have temperature. Okay.
Wow, we used to be a lot colder.
Right. But remember I said that the Earth is 4.6 billion years old? Mm-hmm. Okay, so we're not even getting close with kind of these thousands, because we have to go from thousands to millions and millions to billions. So this actually is just part of the story.
Millions to billions seems a huge jump. It's got to go from millions to tens of millions to hundreds of millions.
I agree. So proxy data is just kind of able to look at data, which actually proxy data should be more like evidence. You know, proxy data. You get data from, for instance, tree rings. And where it's a wimpy ring, you figure they had poor growing conditions that season. And where it's a nice, healthy ring, okay, that you know it was good growing conditions. And if you know something about the species of the tree, you can link that growing condition up to a particular temperature. And water and sun and that sort of thing.
Unfortunately, you have to cut the tree down to do that.
That's true. That's true. I've never been out to see these. Has anybody in here ever seen those big the trees out west? The
redwoods?
Yeah.
No.
I want to go to the redwood forest. Proxy data. Here's some more proxy data. Kind of like we said, sediment at the ocean, but this is actually, and I saw this word and I thought, well, that's missing an L. No, it's not missing an L. It's actually a bog. Okay. So if you have a nice still body of water, like a lake or a bog, it can kind of do, basically year after year, get a fresh sediment that kind of lands on the bottom. Now, it doesn't make sense to go out to the Mississippi River, right, to take a core of sediment there and to try to make any sense of it because it's so moving and that sort of thing. But with these, actually with your core, with your sediment core, you can go back in time with regard to what sort of plants there were. Again, kind of link that back to the climate at the time. And as far as how far have you gone back, and I don't know if we've talked about this yet in this class, but the element carbon, actually, if anything was living like us, we actually are incorporating carbon into our bodies. When we stop living, that carbon we have is the carbon we're ever going to have because we're dead. Okay? And the thing about it is there is actually, there's something, I think this is right. There is a form of carbon called carbon-14, okay, which means it's kind of like the oxygen-16 and oxygen-18. It's kind of that designation. It's an isotope of carbon. And it will begin to, when we're living, we get to add carbon-14. Carbon-14 is relatively unstable, and so once we die, it's a ticking clock. It's going to start decomposing, okay? Yes, it will have a half-life. And so basically we can assess that organic material, that stuff that was alive, and see how much carbon-14 it has left, and go back and date what its date is. But it has to have been living. You can't use carbon-14 dating with like a rock that never was alive. So pollen season, right? This to me kind of slide goes along with kind of the bogs and the lakes. You can kind of diagnose what sort of creatures were growing at that time. Okay, so that was proxy data. Now we're going to talk about why would a climate change? And one of the reasons a climate would change is this plate tectonics that you might be familiar with. So I'm going to show you a slide here, but basically what that slide's going to show you is that, I love this part of it's really kind of more like geology, okay? But, let me say this. I think this is right. So these land masses, these continents, okay, used to be together in a thing called Pangea. And we know that because actually there are kind of like railroad tracks, glacier marks that kind of connect up that rolled over both of them. Yeah, they can fit together. Okay. So this idea of continents moving, granted they moved over a long course of time. Okay. So this isn't necessarily Pangea, but it's kind of broken up into, you kind of see the initial breaking up of the continents. This is what it is today. This white right here, down here on the bottom figure, is kind of showing you what I was telling you about you can see these railroad tracks kind of here with regard to glacier motion. So they really used to be together. So you figure several things happen when a continent relocates with regard to the equator. If it's getting closer to the equator, it gets a warmer climate, right? The other thing is actually this sort of plate tectonics is great at building mountains. And if you build a mountain ridge where there wasn't a mountain ridge, then you can go ahead and have interesting things like airflow or graphic lifting. So
can we pause right there?
Mm-hmm.
On the whole mountain thing, they're saying that the recent earthquake in Nepal, actually grew Mount Everest by up to 30 feet.
No way. Oh, that's cool. I mean, bad, but interesting.
Super interesting.
And that's not that dramatic, but did you hear about Yellowstone? That they, Yellowstone.
The lava pool is much larger
right.
than expected.
There's a lava pool here,
larger.
But then there's a lava pool down here. And you're like, dude, if that thing would go off.
It's not going to be a good time.
Yeah, goodbye, North America. No. But I don't think they're looking for that to happen. Okay, so that's one way you can get climate change, right? It takes a couple billion years. Now, this is another way that we can actually get changes in our climate. And it has to do with, if my fist is the sun, it basically has to do with kind of this relationship between the earth and the sun. So we have a couple of different things that can go on there. One is there's actually three. One, and I can't remember if this made it to your review sheet. I don't think I've taught all of them. But one is eccentricity. And I know this is not an astronomy class, but we talked about eccentricity. Remember we talked about perihelion and aphelion, the fact that that it's kind of the sun is off center from the Earth's orbit. Okay, so that varies, eccentricity. That's all that is. Obliquity, I guess it is. We said, that's that middle slide right there. On one of your exams, you told me that the tilt of the Earth's axis is 23.5 degrees. And by golly, that's what you should go with. But can you see here where it's actually 24.5, 22 degrees? Okay, that sort of little bit of play in it, that has consequences. Because we actually said that the only reason the Earth has seasons is because its axis is tilted. Okay, so if that changes a little bit, then you got changes in the sun, the radiation coming from the sun with regard to which part of the Earth gets most and all that sort of thing. The last one has to do with, see the spinning top? Okay, that's trying to kind of show out something called precession. Precession, by the way, is why the Earth's axis of rotation, how do I say, if most people will tell me that the North Star is Polaris, and you'd be right. We all love Polaris, okay, that's the North Star. But that has not always been basically where our Earth's axis of rotation points, the north axis of rotation. I can't remember was it 200? I think so. 260. Maybe it's coming up on a slide. Like 260,000 years ago, actually our North Star was Vega. But my point here is basically it's kind of like it keeps the same tilt, 23.5 degrees, but it kind of cones like a top. That's called precession. So there's this thing called Milankovitch cycles. And what Milankovitch cycles does is it basically takes all three of those, eccentricity, obliquity, and precession, and it kind of looks for a pattern of recycling of something maybe big that can happen because of those three things that affect basically our hot spots or cold spots on the Earth, ultimately affecting our climates. And so they came up with kind of these periods of 19,000 years, 23,000 years, 41,000 years, and 100,000 years to be kind of hopefully maybe even dips, not hopefully, but it's kind of fun when your theory's kind of supported by data, dips in Earth's temperatures on those time scales. So another reason we can have climate change is because the sun, not something to do with the kind of the Earth-Sun system, but the sun itself is doing something different. So this did make it to your review slide. So if you want to put a little star here, you can. Okay, there's a couple slides I have to do with sunspots, actually. I think is what I put on your Unit 5 review sheet. So if the sun is extra hot, basically the Earth's going to feel the brunt of it. If the sun is kind of on a cool side, the Earth is going to feel the brunt of it too. The sun does this 11-year cycle thing. So every 11 years it ramps up. It's called the solar cycle, and then it cools down. It ramps up, it cools down. And we know kind of how it is in its cycle by tracking its sunspots. There was something called the Maunder minimum, and it was between the years 1645 and 1715, where the minimum here means minimum number of sunspots. I'll just put no sunspots. Okay, for a period of time, let's see, what's 50, 65? So it's like 70 years? Okay, so for 70 years, and it's supposed to be an 11-year cycle, there was no sunspots. And the consequence was it was cold. Okay. Actually, this is oftentimes, it's on the next slide. If it's not, this is oftentimes called the Little Ice Age. Little Ice Age in Europe. Okay, so what the sun's doing can have kind of a long-term effect on us. So you kind of see this dip down here. That's the Maunder minimum, the Little Ice Age minimum number of sunspots. But you can also kind of see these spikes, dips, spikes, dips, spikes, dips, spikes, dips. Okay? That's like the 11-year cycle. Oh, and by the way, this isn't related to this, but when we have lots of sunspots, that's when we're going to get our solar flares. And there's another thing called, do we talk about this? Coronal mass ejections. Those are the solar storms, collectively called solar storms. That's when we can get our cool auroras, and it can also play havoc with our communications and kind of put things at risk almost. Okay, so what do sunspots look like? Well, actually, this right here is what they look like close up. So that's a sunspot. Okay, this kind of stuff over here, it's called actually granule, solar granule, and that's normal, but this is not normal. All right. So we talked about plate tectonics, the sun doing something different. Now let's turn our attention. We're kind of ramping up to actually a little bit. Those weren't human influence, were they? So now we're ramping up to something that is human, possibly related to humans. This actually doesn't have to do, well, it does have to do with climate, but if you've ever heard of the hockey stick, Al Gore's hockey stick, I don't know if that looks like a hockey stick to you, okay? But that abrupt kind of change in the amount of carbon dioxide in the Earth's atmosphere, it kind of starts to set in about the time of the Industrial Revolution. So we start burning fossil fuels, and we start getting carbon dioxide in the atmosphere. I know we talked about this because we talked about the Hawaiian island, the guy taking carbon dioxide levels. Okay. So that was kind of the short-term carbon dioxide concentrations. So if we look, though, historically, carbon dioxide has definitely kind of gone up and down and up and down and up and down. So the way you read this graph is this is today. Okay, so this is us here today. Okay, and then this is going back in time. And you can see carbon dioxide has definitely kind of done its swings. But what's alarming is basically it's never swung this high. I know that, and that was 2011, and so actually there was a milestone. I don't know if you guys heard it too. There was a big sad milestone when we went up to 400 parts per million carbon dioxide in the atmosphere. So that's kind of what we're concerned about. So in the previous chapter, in chapter 13, we talked about air pollution. And we said, and I had to kind of convince myself of this, actually we said one of the biggest air polluters is basically people just driving our own vehicles. Now I know that says 8,000, almost 9,000 pounds, okay, but that's per week, okay. This right here, for instance, this is 17,000 pounds per month. So to me, in order to kind of get the amount we use for electricity, kind of scaled with our driving cars, you have to take that number times 4. So 9,000 times 4 is definitely more than 17,000 pounds. So that's kind of how it goes. So that carbon dioxide that we're seeing increase since the Industrial Revolution, this is kind of today where that carbon dioxide is coming from. So note now, this is talking about temperatures. So this figure down here almost looks like our El Nino La Nina map that we looked at before, to kind of look at where the hot spots were in the southern oscillation. But if you look closely, down here it says temperatures differences compared to the 1951 to 1980 mean. So right here, if it's white, that means no change. Anything over here to this side means actually it's getting warmer. Anything kind of a bluish means it's getting colder. So actually there are some places getting colder, okay? But to me, there are definitely some places getting warmer. So I don't know how they do it. It must be like a statistical thing. But basically you can take a snapshot of the Earth at a given time in a given year and come up with one temperature. And that's kind of what this figure is right here. Okay, so basically you can kind of see the temperatures are increasing worldwide. Are they increasing everywhere? No. Is the average increasing? Yes. So carbon dioxide is a greenhouse gas. It comes from burning fossil fuels. Here are some other greenhouse gases that don't necessarily come from burning fossil fuels. Methane, and I don't know if you remember, gosh, it's been several years now, but there was actually talk of putting a tax on people who raise cows because those cows put out methane, making them to pay for that pollution. I thought this was interesting. We don't eat a lot of rice around here. I don't know about you, but I don't eat a lot of rice. But what's that?
I eat a ton of rice.
You eat tons of rice? There's a lot of people in this world that...
I buy a 50-pound bag.
Wow, you eat a lot of rice.
Because that's great for you.
Isn't there like some kind of disease you can get for eating too much rice? Or you get sick?
I don't know.
I don't think
Might want to
so.
look into that,
I
Kane.
mean, I eat a ton of rice and I never get sick. So.
He looks pretty healthy, but I don't know.
Trust me, no, I drink way too much
It's
beer
kind
to
of
be
like
healthy.
you could overdose on
I
rice.
try to counteract all that rice.
But the growing of your rice is actually adding to the greenhouse gases. Okay, so we talk.
Maybe I should eat less rice.
Yeah, you maybe should. Now, this actually did make it to the test too. So the thing I'm going to talk about, positive feedback mechanisms, will be on your test in some way. Actually, we talked about this earlier in the course, where something is called a positive feedback. If you do something, you have occurrence A, and after occurrence A makes B occur, and actually B reinforces A. So it's kind of like it's called a positive feedback mechanism. A negative feedback mechanism is A occurs, and A makes B occur, and actually B in and of itself does not reinforce A. So with a negative feedback mechanism, basically, actually, it does quite the opposite. It tampers down what originally occurred, A. So negative feedback mechanism, something's going to kind of dwindle down to nothing. A positive feedback mechanism means it can escalate, I guess is a good word. So if we look at global warming, actually there's a positive feedback mechanism, potentially, it's stronger, and there's actually a negative feedback mechanism I'm going to show you with global warming. But here's how this works. If we start with, let's see, where should we start? Let's start with this one. The oceans are warmer. Well, if the oceans are warmer, okay, then actually you're going to have a longer melt period of time where that ice can melt, okay, and ultimately that ice will melt, okay, and as that ice melts, you are actually going to end up with something that's darker colored instead of ice. It's brown, and so actually it's going to be less reflective. And if it's less reflective, we talked about its albedo is going to be less, and then actually it's going to absorb more radiation. And if it absorbs more radiation, then actually it's going to enhance the oceans getting warmer. So that's a positive feedback mechanism. Okay. A negative feedback mechanism, also with global warming, could go something like this. Okay, so again, worldwide temperatures are increasing. As temperatures increase worldwide, then that will mean that evaporation can kick into overdrive. With more evaporation, you would expect to have more cloud cover. With more cloud cover, actually one of the things we know about clouds is they can block incoming radiation. And with some of that incoming radiation blocked, we should have global cooling. Okay, so this is a negative feedback mechanism where actually global warming should ultimately kind of peter down. Speaking of cloud cover, okay, actually aerosols can work as a cloud cover. I think I've heard this kind of strange idea from other people. Basically, put something, if we're feeling extra warm, okay, just put something between us and the sun, okay, whatever it is. Just have it out there, okay. Actually, while it's out there, you might as well have it collecting solar energy and then feeding that solar energy to us. So, I don't know. But it's a thought. This is a picture of, and I was going to look at this. Somebody help me out. Where is Taiwan compared to China? Is it like, because I'm going to see if these were the easterly trades. Okay, there's Japan. Taiwan. Okay. Oh, let's see. Now they're in the Faroe. They're in the Faroe cells. I think it should be a western. Yeah. Okay, that works. So actually, the prevailing wind is taking all that pollution that's creating those wonderful things we buy from China. Okay. And moving it downstream. So there's the corridor of haze. Aerosols, stopping some of the solar radiation from global warming, maybe. I don't think it's the route to go. So we have global warming, we know, because our average temperature of the Earth is increasing. We have global warming because we know ice cover is less. We have global warming because we actually see our sea levels rising. There are a bunch of sad stories out there, and I almost got some and kind of brought in a video, but I kind of got sidetracked. There are a bunch of sad stories about there, especially islanders who had a perfectly good island in the middle of the sea, and now their island is covered, is much smaller than it used to be. So the sea levels rise for two reasons. One is because those ice sheets or the glaciers at the poles are melting, and the other is because if you take water and you heat it up, water will expand. Okay? So two reasons for sea levels rising. And how do we know sea levels are rising? Well, we have these floats, okay, to kind of watch the floats go up. And actually we can get information from satellites too. So this kind of shows you, I was looking at this at my office. To me, this would look like our East Coast. If you've ever been to the East Coast, I know a lot of you have, you kind of see those gentle sort of beaches. And this would be like our West Coast. Kind of abrupt, and actually that has to do with kind of the plate tectonic thing too. But as our sea levels rise, some places are more susceptible to flooding than others. Okay? So the ice sheets are getting smaller. So NP stands for the North Pole. Hey, Santa. And you can kind of see the orange and the blue kind of cover here. This is like the orange. Oops, I used orange to show orange. This is like the orange, and this is like the blue. Kind of showing you the extent of the sheet in 2010 versus 2000. Okay, so this actually is showing you how the sheet is getting smaller. Now, this is the Arctic. Now, I think the Antarctic's been in the news the last 6 to 8 months saying, the Antarctic sheet is getting larger. And I kind of tracked that down, and it didn't take much to convince myself that that's an anomaly. I mean, I don't know if it's an anomaly, but we still have an issue with global warming. Okay. So we talked about tundra. And in the tundra, we talked about permafrost. So I don't know if you see, but I'm going to show you a positive feedback here. And it goes something like this, related to the permafrost. As our global temperatures increase, some of that permafrost thaws. And the thawed permafrost is less reflective, so it'll absorb more of the sun's energy. And then actually we'll have more global warming. So that's unfortunately a positive feedback mechanism in that E-type climate that we looked at earlier. It's funny because sometimes students, when they talk about positive feedback mechanisms, they think, well, positive must mean something good happens. Well, it can if you're trying to train a dog and give him treats and he keeps doing what you tell him to do. But so this is the last slide, and it just kind of emphasizes some things all related to global warming. I know it's kind of hard to read, but it says that we'll have higher maximum temperatures, we'll have higher minimum temperatures. Okay, our precipitation will vary. Actually, notice that some regions will have precipitation, excess precipitation. Some regions will have drought. Now, yeah, exactly. Now, I have heard recently, with regard to hurricane activity, I heard somebody said, be careful with connecting hurricane activity with global warming, just because that may or may not be the case. So, cool. Well, that ends that.